The James Webb Space Telescope, JWST, is the most sophisticated space observatory ever constructed, breaking the frontiers of contemporary astronomy and cosmology. JWST, launched in 2021, has already started to transform our perception of the universe by viewing it more vividly than any previous telescope. With its unprecedented infrared capabilities, JWST enables scientists to look further back into the universe than has ever been possible before, opening up new information about the development of galaxies, stars, and planetary systems. Perhaps the most revolutionary feature of JWST is its capacity to look back in time, offering a glimpse of the early universe, the so-called cosmic dawn. This era, which took place between 300 to 400 million years since the Big Bang, is a turning point in the evolution of the universe where the first stars and galaxies were starting to be created. To better understand how important JWST's observations are, it's important to realize the significance of the cosmic microwave background, CMB. The CMB is a weak radiation that fills the universe and is a remnant of the Big Bang. It is regarded as the universe's oldest light, taking a snapshot of the universe at the age of 380,000 years. Through the analysis of the CMB, researchers have been able to create an elaborate model of the early state of the universe and its subsequent development. Information collected from the CMB has played a central role in influencing our knowledge about the universe, serving as the basis for numerous cosmological hypotheses. And whereas the CMB shows us the universe in its earliest moments, the observations of JWST reveal more about the era referred to as the cosmic dawn. In this epoch, the universe went from being dark and homogeneous to being illuminated and structured. The first light of the first stars illuminated the universe and galaxies started to take shape. The way JWST is able to receive the light of these distant ancient galaxies is one of the most awe-inspiring abilities. These galaxies lie at great distances from us, so effectively what we are viewing is like a look into the past when seeing them. By observing the light radiating from these galaxies, astronomers can gain insight into how stars and galaxies developed early in the universe and give us essential knowledge of what processes gave rise to the universe today. Perhaps the most striking thing about JWST's discoveries is that it found galaxies that are much more mature than they should be based on their age. These galaxies, which were seen at distances that represent times when the universe was but 300 to 400 million years old, appear to have developed structures and elements that we would normally look for in far older galaxies. This has opened up a number of interesting questions regarding the speed and efficiency with which galaxies have formed. Are galaxies perhaps beginning to form sooner than we thought? Or did they grow more quickly than today's models of cosmic growth suggest? These issues trouble conventional wisdom on galaxy, star, and other cosmic structure formation over time. To meet these challenges, researchers are looking to alternative models and theories. One of the main models used in cosmology is the lambda CDM model, comprising dark energy, lambda, cold dark matter, CDM, and the Big Bang with cosmic inflation afterward. This model has been extremely successful in describing a lot of the universe's evolution. The lambda CDM model has come under pressure recently, though, especially regarding the formation of early galaxies. The finding of mature galaxies at a very early stage indicates that galaxy formation might have happened much quicker than the standard model suggests. This may mean that there are gaps in what we know now, or that galaxy formation processes were more intricate and quicker than we had assumed. One way that these discrepancies might be explained is that dark matter, which constitutes approximately 27% of the universe's total mass, may have a greater influence on galaxy formation than we currently know. Dark matter has never been directly observed, but its effects on visible matter through gravity are well documented. For years, scientists have made educated guesses about what dark matter is and how it behaves with regular matter, but its nature is still a mystery. The swift creation of huge galaxies that JWST has observed could be attributed to dark matter in ways we've not yet been able to fully comprehend. This would mean that JWST observations could reveal new, essential information that aids scientists in streamlining their knowledge about dark matter and how it assists the universe in evolving. Another option is that the history of the Big Bang would have to be rewritten. The observation of galaxies that look older than they are indicates might mean that galaxy evolution started before the normal Big Bang model predicts. This would entail a major overhaul of the underlying assumptions regarding the timeline of the evolution of the universe. Certain scientists have even suggested that the Big Bang itself might not have been the real start of the universe. Rather, they put forward the theory that the universe could have expanded and contracted repeatedly, with every cycle representing a new Big Bang, which gives birth to a new universe. This concept belongs to the cyclical universe theory, which disputes the conventional idea of a one singular Big Bang as the universe's genesis. Aside from these more revolutionary theories, scientists are also researching adjustments to the standard model of cosmic inflation. Cosmic inflation is the hypothesis that the universe went through a stage of incredibly rapid expansion in the immediate aftermath of the Big Bang. This theory has been successful in explaining many aspects of the early universe, but some details about inflation still have not been resolved. Some scientists are looking into models of inflation that may explain discrepancies in the development of early galaxies. Models could involve concepts such as differences in the speed of light or changes to the laws of gravity. These concepts could offer a more comprehensive picture of the universe's initial development, perhaps illuminating the processes that rule the development of galaxies and other galactic structures. Among the most thrilling prospects to emerge from JWST observations is the possibility of revealing new physics to account for the irregularities in galaxy development. Other scientists have suggested that perhaps there were new types of energy or forces operating in the early universe that we don't yet know about. For instance, the existence of very massive, mature galaxies so far back in the universe might be due to new types of dark energy or new interactions between dark matter and normal matter. Alternatively, new gravities or theories of quantum mechanics could fill the gaps in the puzzle, illuminating the causes of the high-speed galaxy formation and the inconsistencies detected by JWST. More data from JWST and coming space missions like ESA's Euclid and NASA's Nancy Grace Roman Space Telescope will, undoubtedly, help to better understand such discrepancies. These missions will provide more detailed observations of distant galaxies, the cosmic structure, and the expansion of the universe. The data collected will help confirm whether the anomalies observed by JWST are real or if they are the result of observational errors. If these discrepancies are confirmed, it could signal a paradigm shift in our understanding of the universe, forcing scientists to reconsider long-standing theories and models. Finally, the James Webb Space Telescope is revolutionizing the science of cosmology by opening doors to new knowledge of the universe's earliest moments. The observation of galaxies that are more advanced than anticipated has provoked significant questions regarding galaxy formation speed and process. Such observations refute the current lambda CDM model and have prompted researchers to venture into new concepts and alternative models. The likelihood that we will have to update our conception of the Big Bang timeline and cosmic inflation is an intriguing idea, as it would pave the way for new theories and advancements in physics. As JWST continues to collect more data, we can anticipate yet more surprises that will redefine our understanding of the universe and how it began. The revelations by the James Webb Space Telescope, JWST, in recent years have stunned the science world, and many questions have been raised on galaxy formation and evolution. While the telescope is looking farther into space, it has revealed surprises that contradict our present understanding of how galaxies, stars, and other cosmic shapes evolved in the distant past. One of the most dramatic observations is the identification of galaxies that look much more mature than we would anticipate based on their age. These galaxies, seen when the universe was only 300 to 400 million years old, indicate that they are much more evolved than our galaxy formation models would suggest. This has made many scientists wonder if our present cosmological models, especially the lambda CDM model, must be corrected. The lambda CDM model has dominated modern cosmology for decades. It describes the large-scale structure of the universe and includes crucial elements like dark energy, lambda, cold dark matter, CDM, and the Big Bang followed by cosmic inflation. This model has been able to account for a great many observations, but the new findings discovered by JWST have put it under greater scrutiny. The detection of mature galaxies at this point in the history of the universe is raising several key questions. How were these galaxies able to form so rapidly? What were the processes at work that enabled them to evolve so quickly? These questions raise the possibility that the assumption that it takes billions of years for galaxy formation to produce the level of complexity we see in these older galaxies is wrong. Scientists are considering several possibilities to answer these questions. One is that the early universe had conditions different from what we assumed, and therefore galaxies could have formed more rapidly than anticipated. Maybe the first stars and galaxies formed under more favorable conditions than the current models suggest, or perhaps they had access to more efficient processes that sped up their formation. One theory getting some purchase is that the early universe was more densely filled with gas, something that could have promoted faster star formation and quicker galaxy evolution. Another option is that dark matter, which is assumed to constitute some 27% of the mass of the universe, was a more significant influence on galaxy evolution than we knew before. We know dark matter's gravitational impact on normal matter, but nobody knows what dark matter is exactly. The higher concentration of dark matter in the early universe may have created the conditions necessary for galaxies to develop at a much quicker pace. Another major consequence of the JWST findings is the necessity to rethink the timeline of the Big Bang. The Big Bang traditional model, which holds that the universe arose from a single point of extreme density about 13.8 billion years ago, has been at the forefront of our cosmological knowledge. The Big Bang theory timeline may have to be adjusted, though, in light of the existence of galaxies that are seemingly much older than their own age indicates. If they did form earlier and more rapidly than predicted, scientists would have to re-evaluate how the universe developed in its very first years. One way scientists might explain this inconsistency is that the early universe went through cycles of expansion and contraction, as opposed to a single Big Bang event. This cyclical universe theory suggests that the universe might have passed through multiple Big Bangs, each followed by a contraction, giving rise to new galaxies and cosmic structures. Although this remains speculative, it breaks the conventional notion of a single origin for the universe. As scientists strive to improve their understanding of the early universe, one of the most fascinating possibilities is that new physics is involved. The surprise sudden acceleration of galaxies could be a sign of unfamiliar dark matter and dark energy interactions with normal matter. A few scientists think the rules of physics in the early universe were different and that galaxies formed more quickly than they do today. For instance, theories that suggest that the speed of light could have varied in the past could explain the accelerated evolution of galaxies. In the same vein, alterations to our current gravity models could shed new light on how the formation of galaxies and other structures came about. These concepts could redefine the nature of cosmology and accommodate the inconsistencies between JWST's findings and the lambda CDM model. One of the challenges in cosmology is that many of the ideas currently being proposed are highly speculative and hard to test. The early universe was a very different universe than the one we see today, and many conditions present at that time are hard to recreate in the lab or even with computer simulations. This makes it difficult to test alternative theories of galaxy formation and cosmic evolution. But the information collected by JWST and other future missions, like ESA's Euclid and NASA's Nancy Grace Roman Space Telescope, will shed more light on what might refine the scientists' models. Future missions will emphasize collecting more refined observations of faraway galaxies, the structure of the cosmos, and the accelerating expansion of the universe. With more data, scientists may be able to determine whether the discrepancies observed by JWST are real or simply the result of observational errors. Another key aspect of JWST's discoveries is the potential impact on our understanding of dark matter and dark energy. These two mysterious components make up about 95% of the universe, yet they remain largely invisible to us. Dark matter is thought to exert gravitational forces on ordinary matter, though we have not detected it directly. Dark energy, however, is postulated to be accountable for the accelerating expansion of the universe. Both dark matter and dark energy have been incorporated in the lambda CDM model, though we know little about them. JWST's capability to image faraway galaxies and the early universe stages might shed light on the nature of these mysterious substances. For instance, if dark matter's contribution to the genesis of nascent galaxies was greater than initially assumed, it would lead to a greater understanding of how it combines with regular matter. Likewise, if dark energy was responsible for driving the development of the universe, JWST observations may provide insight into its nature. Aside from its contribution to cosmology, JWST results also have implications for learning about the origin of life. The study of the early galaxies and stars can teach us more about the conditions in the early universe, which could have contributed to the formation of planets and the possibility of life. Scientists can learn more about the components of life and how they could have formed in the early universe by examining the elements and compounds found in the early galaxies. This may give us some useful insights into the origin of life on Earth and the possibility of life elsewhere in the universe. As scientists continue to study the data from JWST, it's obvious that we are on the threshold of a new era in cosmology. The findings so far have already transformed our knowledge of the universe, and there is still much to discover. Whether we will need to rethink the lambda CDM model or come up with entirely new ideas to explain JWST's anomalies is not clear yet. However, this one thing is, the universe is much more mysterious and complicated than we ever dreamt, and JWST is providing us with the tools to unlock its secrets. As upcoming missions and new observations expand on the information gathered by JWST, we could soon find ourselves on the cusp of a tremendous leap that will forever revolutionize our understanding of the universe. In summary, the James Webb Space Telescope has already made tremendous inroads into our comprehension of the early universe. The observation of galaxies that are far more mature than predicted puts into question our current cosmological theories and poses key questions regarding the nature of galaxy evolution. Such observations have encouraged scientists to pursue alternative theories and models that would explain the speedy evolution of such old galaxies. As we collect more information from JWST in future missions, we can be on the threshold of a new era in cosmology that will answer some of the most basic questions about the universe and its creation. Whether or not these answers will validate our existing models or make us question everything we think we know, it is yet to be seen, but one fact is certain: the universe holds many secrets yet to be discovered. In the universe. As scientists continue to study the data from JWST, it's obvious that we are on the threshold of a new era in cosmology. The findings so far have already transformed our knowledge of the universe, and there is still much to discover. Whether we will need to rethink the lambda CDM model or come up with entirely new ideas to explain JWST's anomalies is not clear yet. However, this one thing is, the universe is much more mysterious and complicated than we ever dreamt, and JWST is providing us with the tools to unlock its secrets. As upcoming missions and new observations expand on the information gathered by JWST, we could soon find ourselves on the cusp of a tremendous leap that will forever revolutionize our understanding of the universe. In summary, the James Webb Space Telescope has already made tremendous inroads into our comprehension of the early universe. The observation of galaxies that are far more mature than predicted puts into question our current cosmological theories and poses key questions regarding the nature of galaxy evolution. Such observations have encouraged scientists to pursue alternative theories and models that would explain the speedy evolution of such old galaxies. As we collect more information from JWST in future missions, we can be on the threshold of a new era in cosmology that will answer some of the most basic questions about the universe and its creation. Whether or not these answers will validate our existing models or make us question everything we think we know, it is yet to be seen, but one fact is certain: the universe holds many secrets yet to be discovered.